me to ask about, because it's a little disappointing, to be honest, when I looked at on the homework. I mean, I did 28B, a lot of it for you, totally setting it up, whatever. It looked like some of you finished that one, or maybe partially finished that one. Then we talked, we kind of said at 28C, and some of you didn't have any more work done on 28C. Not a single thing more than what I had put up on the board for you yesterday, or on Friday. So, I mean, that was a little disappointing, because it's pretty much like 28B. I mean, it takes a little while. I mean, it might use half a page, 3/4 of a page. Somebody didn't have very much written down on that at all. So, and I know it's an even one, so, but, you've got this as well. So, anyway, we have to make some strides on that probably to do the optimization problems by the time we get to the quiz next week, and that means coming in and getting some help. Make sure you do that. Make sure you do that. So, anyway, we had our steps that we were supposed to go through. I suppose let's maybe save 19 and 21 here a little bit for the end. So let's look at 27, I guess. Let's look at 27. That's probably the easier of the bunch. And that was another one that was a little, and I know in the homework you don't maybe show every step that you should. I mean, I think you should. I mean, on the quiz you're going to have to. So make sure you're doing that. So on 27, it says a piece of wire 100 centimeters long is going to be cut into several pieces and used to construct the skeleton of a rectangular box with a square base. Okay, well, so right there you go, just rectangular box, square base. So I let X be the bottoms. Okay, and so you're going to have, so hopefully everybody understands where this equation comes from right here. That we got 1, 2, 3, 4, 5, 6, 7, 8 pieces that are X long and of wire, and then we have 1, 2, 3, 4 pieces that are Y long, and we have 100 centimeters of wire. So those have to add up to 100. Okay, and we're trying to maximize the volume of the box, and so again, same formula we had on 28 that we set up together. So X times Y is what we're trying to maximize, and so we're going to solve that for Y and get that. So we put that in there, and we get this. So step 1, of course, was identify what we want to maximize, which is volume. Step 2, write and label an equation of that quantity, which is what we did right here. Step 3 was get it in terms of one variable, which we did using this information. Step 4, check your different places. Derivative undefined, where does a derivative equal 0, which gives you these two answers here. And then any endpoints. Now what I didn't put down were endpoints. I put them in here. So again, let's review that. How do you get endpoints? What's the smallest? In this case, our input is X. So you always look at the input, right? It's always your X. It might not always be the letter X, but whatever your X or your input variable is, what's the smallest it can be? So what's the smallest X can be? Well, it could be nothing, okay? Which you could argue, is not really a box, but usually we go ahead and put it there. And then what's the biggest? Now that's the one sometimes people have trouble with. Well, typically if there's two variables, the biggest this one could be is when this one's the smallest, right? Because we got a fixed 100 centimeters of wire. So if we use it all for X, there's none left for Y. If we use it all for Y, there's none left for X, right? So if we don't use any wire for X, then that means all 25 centimeters on each of those 4 sides, right? We use it all for that. So that would be the littlest X would be 0. The biggest X would be when Y is 0. So that would be 100 divided by 8. And that's where I got 12 and a half. Okay, so the biggest X could be 12 and a half. All right, so that's how you find the endpoints typically. What's the littlest X could be, what's the biggest, and usually the biggest it can be is when the other variable in there is the smallest. Now, it's not always that way, but a lot of times it is. Okay, well, anyway, makes sense that if Y is 0, we have no volume. If X is 0, we have no volume, so it kind of makes sense. So whatever you got for putting 25 thirds in there, and again, it turns out to be a cube, not a surprise. Okay, not a surprise, but we got to be able to go through those. Okay, so that was the largest volume. Then it says, what are the dimensions of the box with the largest surface area? Okay, so, If it's a box, I'm probably not giving you those formulas. You know, a cylinder, maybe I would. If I thought there was a question of whether you should know it or not, maybe I would give you that formula. Surface area. How do you find surface area of a figure? You just add up all the surfaces. Okay, so what's the area of that front right there? XY. How many of those are there? 4 of them. What's the area of this surface? X squared. How many of those are there? 2 of them. So you add that up. 2x squared plus 4xy. Okay, surface area of a figure, unless it's a sphere or something circular, that's a little trickier, so I may give you that. Okay, once we've done a couple, though, you should have it. But okay, so that's what you're trying. So on part B, you're trying to find the largest surface area. So we're trying to maximize that. Now we still have the same amount of wire. So it's still that same y equals 25 minus 2x. So I substitute that in right there. Okay, and it all simplifies to that. Now that's an upside down parabola, so it's pretty clear that's going to be a max. Again, trying to start with just some pretty simple equations that work out pretty nice. Okay, before we get into something a little trickier. So you got this, and so that's what we're trying to maximize. We do the derivative, we set equals 0, guess what? It's going to be a cube again, right? I mean, but again, that doesn't matter. I mean, right now, the steps are the steps. So this is never undefined. A prime's never undefined. Remember, we always look where A prime is 0, where the derivative is 0, where the derivative is undefined. That's where your max and mins are going to be, or maybe at endpoints. That's why we're checking endpoints, right? Max and mins are going to occur at one of those 3 places, okay? So again, endpoints are really the same, you know, plug 25/3 back into your area, that's your max area. Although it said what are the dimensions is what they asked for. So your answer should really look like that, and it should probably have, it should, not probably, it should have units on it, right? I think those were centimeters. Okay, so the dimensions are what they want. So 8 1/3 by 8 1/3 by 8 1/3. And it came out the same on 27. Okay? All right, so let's talk about 19 and 21. I think these are really good. This is where you start to get into something a little more interesting type of problem, a little bit, even though they did keep it fairly simplistic in the scenario, not simplistic in solving it necessarily, but I mean simplistic in the scenario. So in 19, they give us this equation right here, and they say this is for a projectile leaving the origin with initial velocity v sub 0 aimed along the line y equals mx. So we're talking about this. So here's this would be like your x and y axis. So when they say the y equals mx, they're really saying, they're giving you the angle, right? They're giving you the angle that it's launched at. Okay, so basically if you know the angle it's launched at and its initial velocity, we should be able to follow its path. At that point, once it leaves, once this is gone, whether it's a baseball thrown or a shot put or whatever the case may be, okay, it's going to follow then a parabolic path. Okay, I mean it's just law of physics. Okay, because its gravity is essentially what's affecting it at that point. Okay, so they say, well, and they give you this equation. Okay, this is going to be the parabola. This is the parabola. If you look at that equation, it's a parabola. X, it's got an x squared in it. Okay, so if we're going to throw it, they said let m equal 1. So this is a football. We're doing a football this time. Okay, so 30 meters per second. Put that in there. 9.8 for gravity. And what's m equals 1 mean? Slope of 1, which would be, if we're going to change that to an angle, 45 degrees, right? So we're going to kick it at 45 degrees, okay? But in the equation, that simplifies the equation a little bit to put it in as an m instead of an angle. If we put it as an angle, then we got to put tangent, tangent of theta and so forth, right? Because what's tangent of 45 degrees? 1, right? So this equation would be tangent squared theta in here, which just makes it a little more difficult. So that's where one of the reasons I'm saying they simplify it a little bit. So they put m in. All right, now, and we've talked about that, right? Tangent is opposite over adjacent, right? Which is rise over run, right? So the tangent of an angle is the slope of the hypotenuse, right? Those two things go together. All right. Anyway, so then what you were supposed to do is just, okay, how high does it rise? So you can just go ahead and do the derivative of that. Set it equal to 0. You get x equals, what'd you get? You get something. 45.918. Okay, now that's this direction now, right? So when it hits its peak, x is 45.918. So the y value of that is 22. What do you got there? 9 what? 959. Okay, so I mean that's pretty clear. Again, a rationale. Now, you know, if we're, where does it land? It didn't really. This one doesn't sound like a max problem. It is. It's the max height. What's the max height? How high did it go? It's really doing that. You know, again, this is, you know, y prime's never undefined, that kind of thing. We have a single candidate. You know, this would be one I'd clearly say, hey, this equation's an upside down parabola. You know that it's quadratic. So therefore, it's going to have a max here when the derivative is 0, only 1. That's it. That's what it's got to be. That could be your justification, okay? Because it's a pretty simplistic scenario. All right. Where does it land? What would you do for that? Put a 0 right up here and solve, right? And so write that out, though. 0 equals da-da-da-da-da. So this is a lot like our parametric equations, a little bit, except it's in terms of x and y, right? Instead of the t's, but it's kind of that same feel. Put a 0 in for y, where's it land? And obviously it's just going to be double that number, right? Because again, it's parabola. We shoot it from the origin. There's going to be symmetry. High points at 45.918. This is going to be double that because of symmetry. Okay, that's pretty easy. But again, solve it. That'd be great. All right, plot the trajectory on and on. Okay, so 19 is not that important. 21 is the problem that is the part that's interesting. Okay, so we go to 21, and it says, well, let's just look at this. Okay, it says, in the situation, this projectile has this range of r equals. The range is the horizontal distance covered before landing. Use the formula in exercise 19 to show why the range formula holds. Okay. So what I want to say to you is in this equation, which one of those letters is R? The X. It says R, the range is a horizontal distance covered. So all we need to do is take this equation and stick an R there and there. And it's how far it goes until it lands. So what's Y? 0. So what we need to do is we need to take the equation in 19 and we need to put an R here. Well, I didn't put an R here. I just said I'm going to pretend there's an R here. I'm going to solve for R. In other words, I'm going to solve for X. So I'm going to put a 0 there, and I'm going to solve this for X. Okay, well, what I do, I take this big glob of stuff here, and I just add that over. So I get this on this side. Now, I'm going to divide by X. Now, I warned you about that and said you should divide by X. But dividing by X, I just lose what? I lose when X is 0. Well, when is X 0 in this problem? At the beginning, that's your horizontal distance covered. I don't care about that, right? I care about what X is over here when it ends. So I don't care about when X is 0. So I'm going to go ahead and divide by 0. Doesn't bother me, okay? I could have factored out an X up here, you know, and it just said I'll ignore that part of it anyway. Okay, so I divide by X and I get this, and I not only did I divide by X to get rid of that and one of those, but I took this piece and divided by it over here too. Because what do I know about G and V sub 0? As this projectile is moving along, what do I know about G and V sub 0? They never change. They're constants. They're just numbers. So G like pi or the 2, they're constant. They will never change. See, that's what it's saying in here. Is it says in part B, it says suppose that V sub 0 is fixed, but M is variable. So M becomes our variable in this problem, not the X like the last problem. The last problem we did the derivative of Y with respect to X, right? Now we're going to solve for, oh, and by the way, for solving for X, and I just flipped this, inverted and multiplied to get that. So that's exactly what they had said in part A. They said show that that is the range formula. So sure enough, that's what I get when I solve for X. Okay, Now I want to maximize X. Think about a shot putter. Isn't this what they're trying to do? Right? Shot putter is trying to figure out one of the things a shot putter might be figuring out, and this reminds me so much of one of the hardest classes. This might be surprising. One of the hardest classes I took in college, math major, right? To teach math, a lot of abstract algebra, a lot of crazy hard math classes. My two hardest classes I took in college were for my coaching endorsements. You don't even need a coaching endorsement to coach. I mean, anybody can coach, right? I mean, you want to coach? Hey, come coach, right? But they have a coaching endorsement, right? At UNL, they have a coaching endorsement. Well, we get that. Okay, then somebody really want me to coach. That was coaching. Yeah, right. So whatever. But I had to take anatomy. I mean, the same anatomy the pre-med majors were taking. It was awful. It was over at East Campus. I wasn't interested in that at all. Matter of fact, Mr. Limbach and I figured out that we were in the same anatomy class. We didn't know each other at that, but we figured out because we were talking one day about this professor that we had. It was awful. Oh man. Anyway, most of the people in there, most of the pre-med majors all took it twice because they needed a good grade, you know, and a C was about the best you were going to do the first time through. And we worked on human cadavers. And, I mean, if you guys have, how many have taken anatomy here? Okay, so so you go in for your lab test on the arteries, and you go in, there'd be the leg, and there'd be these arteries, and there'd be a little string around one of them. And and if you've ever seen arteries and veins and nerves, in the human body, there's a lot of them. Looked like a strand of spaghetti. I mean, there were strands of a box of spaghetti. There'd be a little thing around just one of them, and then you're supposed to name it. My God, I don't know how doctors do it, but anyway, anybody here could be a doctor? Good for you, because I'm not that smart. But anyway, I digress. So anyway, anatomy. So anatomy is a brutally hard class, and then it was even weirder because the professor was this real serious, kind of hard-nosed guy, and he had an eye condition, so he was sensitive to light, so he had to wear dark sunglasses all the time, indoors. So he just kind of, so you're in there and you're in the lab and working on human cadavers. You got this teacher with these creepy dark sunglasses on. It was just, the whole thing was bizarre. But anyway, that was one of the very hard classes I took in college. The other one was biomechanics, physiology, basically. And it was basically physics of motion and things like that, kinesiology. It was kind of a combination of those things. And so we did all of this kinds of stuff, all this kind of physics, and it wasn't calculus based, but there was a lot of stuff. So you think about this, I mean, as a track coach, so you think about a shot putter, you think about a long jumper, right? It's kind of the same thing, right? So what we're trying to find is what slope, what angle is the optimum to go the farthest? What angle should I launch the shot with? What angle should I jump off the board to maximize this? Okay, that's really what this problem is. Okay, so that's the variable, that's the input variable. This is the output variable. Okay, and these are just constants, so that's why they wrote it like this. So when you're going to do your derivative, you just got to think of this as a number hanging out in front. It just stays there, and now you got to do this. Well, what do you got to do the derivative of that? How do you do the derivative of that? Quotient rule, right? We're going to do the quotient rule. Okay, all right. So we go over here, go to the next step. So we're just going to leave this alone, leave this hang out here, do the quotient rule. Derivative, that was r. I changed that from an x to an r now. Okay, so we want to do the derivative, see where it's 0. So derivative top is 1, leave the bottom alone, minus the top left alone, derivative bottom is 2m, bottom squared. Okay, so that's still hanging out here. This would be 1 plus m squared minus m squared, so that's 1 minus m squared equals 0. Well, this is never going to be 0 because you're going to have some initial velocity. Gravity, is always going to be 9.8. When is a fraction 0? When the top is 0, so 1 minus m squared equals 0. So that's pretty easy then, actually, plus or minus 1. Of course, we're not going to throw it down like that, so we can eliminate the negative. So the optimum should be what? 45 degrees. So Throw it a little too high, it's going to come short. Throw it too low, it's going to be short. 45 degrees would be the optimum. So if you research like a track and field manual, long jumpers, that kind of thing, they would want to take off at 45 degrees. So I always remember when I first did this problem in calculus class, and I went to Coach Larson, right? So you know Coach Larson from the boys track. And I went to him and I asked him about his shot putters, and then of course R prime ever undefined. This will never be 0 down here, so you have to worry about that. In points, what's the littlest m could be? Well, 0, I suppose, 0 slope. The most, I suppose, infinity. You're not going to throw it straight up. So you could talk about those things and see why this would be your max. Okay, so see, okay, so what about them? So we got it. Now, but so I went to Coach Larson and I asked him. I said, what do you teach those? What do you do? What do you teach those guys for the shot put? 45 degrees or whatever. He says, it's about 42. It's between 42 and 43. Why is that, you suppose? Why do you suppose? We just showed mathematically that 45 degrees gives you the max distance horizontal. Why didn't he tell him 45? Well, that's interesting. No, forget what you said about the arm strength. Think about the first thing you said. In other words, look at my picture here. We don't throw it from ground level on the shot put, right? Now, takeoff from long jump you are, right? Your takeoff foot's there, and you're going to land in the pit, right? Which those should be at the same. But you're actually throwing from maybe, say, here. And what is that angle? And so that also explains why he said, well, it depends. He says somewhere around 42, 43, something like that. Well, mathematicians, somewhere around. What do you mean? What's the exact? Well, not everybody's the same height, right? So the shorter you are, a little higher degree, right? A little closer to 45, maybe 43 something. You're a little taller, 42. Now, to be honest, and so we had a nice discussion about it, and to be honest, though, it's probably not the most important thing. Because a high school shot putter is probably not going to be able to hit 42.5 degrees every single time, right? And keep in mind, there's two other variables in the equation. Of course, we can't affect gravity, and the shot put's heavy enough, it's not going, that's not going to change. Wind resistance is not going to be a factor, right? What's happening? Initial velocity. So, so what's he going to say? Well, instead of working on that 42.5 degree angle, get the weight, go lift weights and make your initial velocity bigger, right? And if you can get the initial velocity bigger, now, you take an elite Olympic athlete, right, who's maybe taking all the steroids they can take and is, as strong as they can be, and maybe they're not going to change their initial velocity. And maybe they do some high def, slow-mo camera, looking at the angle of release, and they tweak their technique just a little bit to change that angle, just a little bit, possibly to eke out an extra 6 inches or something. Maybe at that point, then it does become kind of important. But it was interesting because he, and he admitted when he got it, he had a series of articles and stuff, and it showed, if you're this tall, it should be about this angle, right? And that would just be going through an equation like this and just tweaking a little bit so that it was that part of the parabola. Okay? So anyway, again, maybe because I coach track, but I think that's an interesting problem as well. All right, so let's move on to the new thing we need to talk about today. So if you want to get your notes out, the next topic here in chapter 4, we're going to continue to have opportunities for you to do optimization problems, okay, max and min problems, before a quiz on Friday. So anyway, related rates. So in your notes, if you wanted to write something down about what this section is, section 4.5, I think, in our book, related rates. Earlier, we used a definition calculus as the mathematics of change. We've talked about increasing, decreasing, stuff like that. Change occurs over time. So when we talk about how a quantity changes, we're talking about the derivative of that quantity with respect to time. Okay, so what we're going to be looking at is situations where you have multiple quantities in the same problem that are changing. Okay, now here's a couple of things like here, just to get us into the thought process of this. And again, it says related rates, so we're going to have a lot of things that are rates in these problems. Okay, so here's a few right here. John is growing at a rate of 3 inches per year. It says write the following mathematically. You don't have to write this down, this part now necessarily. John is growing at a rate of 3 inches per year. Write this mathematically. Okay, I'll give you a hint. I'll do the first one for you. That makes sense? What would h be standing for here? His height. His height is changing, so that's h prime. Okay, so one of the important things we will have to do in these problems is identify some rates, label them properly with a letter that's appropriate and a prime. Okay, my mutual fund is shrinking at 4 cents per day. What do you want to call that? F, fund, fine. F prime equals negative, if you want it in dollars, you could go negative 0.04, or you could just say negative 4 if you were going to stay in cents. But it'd be negative, right? Because if F, the mutual fund, is decreasing, then F prime would have to be negative. The radius of a circle is increasing by 4 feet per hour. R prime equals 4. The volume of a cone is decreasing by 2 cubic inches per second. V prime negative 2. Okay, get the idea? So we're going to be talking about these kind of changing quantities as we go along. All right, so let's look at an example here. We're kind of working our way up to what the problems are going to look like. A rectangle is 10 inches by 6 inches long whose sides are changing. Think of it like this. Oops. Isn't that a rectangle whose sides are changing right there? And think about that kind of a situation. I could make it so they're both getting bigger. I can make it so they're both getting smaller. I can make it where one is getting bigger and the other is getting smaller, right? Here they're both getting bigger, right? But here, the width down at the bottom is getting smaller, but the length is increasing, right? So one could be getting bigger, one could be getting smaller, okay? That's the kind of situation we're talking about here. Rectangle is 10 by 6, but its sides are changing, okay? So at some instant in time, it's 10 by 6, okay? Write formulas for both the perimeter and area and how fast each is changing in terms of L and W. So let's let this be my length, and let's let this be my width. So at some instant, the length is 10 and the width is 6, but it's moving, it's changing. So what can I call the perimeter? P equals 2L plus 2W. What would be the change in perimeter? P prime. Now, here's where it gets, this is where we change gears a little bit from optimization. In optimization, one of our goals was to get into a single variable equation because we wanted to do the derivative with respect to, we were going to maximize volume. We want a volume equation, but we wanted it in terms of one letter. And then we would do the derivative of v with respect to that letter. So it would be v prime of x, dv over dx, or dv prime of r, right? With the cylinder one, where you might have had r in there, or h, or whatever. Okay? That's not what we're talking about now. We're talking about all of these quantities changing with respect to time. So as I was dragging out that rectangle a minute ago, you had the perimeter changing with respect to time. You had the area changing with respect to time. You had the length changing with respect to time. and you had the width changing with respect to time, right? So that would have been P prime of t, A prime of t, L prime of t, and W prime of t, or dW dt, dL dt, dA dt. These are all going to be with respect to time. So when we talk about related rates, these are all going to be rates, something per minute, something per second, something per hour. Okay, so back to this. So my change in perimeter is going to be P prime. I'm just going to do the derivative of this equation. Now, again, in optimization, we would never do this because we'd have to do the derivative with one of these. We had to get one variable. That's not what we're doing. We're doing it with respect to time. So do you see how this is implicit differentiation? This is implicit differentiation. P is a function of time. At a given time, that rectangle has a certain perimeter. At a given time, it has a certain length. At a given time, it has a certain width. So there's this kind of hidden variable t here. So what is a derivative of 2L then? 2L prime. Remember, do the normal derivative. Tack on a y prime. Well, now it's tack on an L prime. So the derivative of 2L is 2L prime. If that would have been, well, you'll see it here in a minute. Okay, plus what's the derivative of 2W? 2W prime. Okay? All right. Area. What's the area of that rectangle? Length times width. What's the change in area? That's A prime. What's A prime? How do you do the derivative of LW? L times W. Product rule, right? Derivative of L? L prime. Leave the W alone. Plus, leave the L alone. Derivative of W? W prime. Okay? Now, here's what's going to happen to you in this problem. So in this problem, you're going to be given a problem like this. You're going to say, okay, at a certain instant in time, the length is 10 and the width is 6, and the length and width are both increasing at a constant rate of 2 inches per second. What did they just tell you this to? What can I label this to? L prime is 2 and W prime is 2. They just told me how fast the length and the width are growing. So now we can find the change in perimeter. We can find P prime because of this equation right here. So we can plug a 2 in for L prime. 2 times 2 is 4 plus 2 times 2, and we get 8, and then we got to put units on it. 8 what? Inches per second. Because remember, this 2 was just part of the equation, and this was inches per second. So this is 4 inches per second plus 4 inches per second is 8 inches per second. Now I'm not going to make you keep track of units throughout the problem. You just have to have them on at the end when you're done. And perimeter would be measured in inches, so 8 inches per second. What's a change in area? Well, now we're going to use this equation. So L prime is 2. What's W? 6 plus L is 10 and L prime or W prime 2. So we get 12 plus 20 is 32 what? It's area, it's change in area, inches squared per second. Okay? Now, you can tell from the equation, remember this 2 was L prime, that was inches per second, and W was in inches. So inches per second times inches should be inches squared per second. Okay, so it works out. But if you set up the equation right, you can just at the end say, hey, this is area, so that's got to be inches squared per second. All right? So that means if you had a rectangle that I was dragging out, and the length and width were both increasing at 2 inches per second at the instant, the length was 10 and the width was 6, the perimeter would be growing at 8 inches per second, and the area would be growing at 32 inches squared per second. But those aren't constant, right? I mean, it's not going to continue at those. You can imagine, take that rectangle and drag it out at a constant rate. You can see as that rectangle gets bigger and bigger, that piece of area you're adding on is getting less and less significant, isn't it? This is probably going down. right? I mean, not growing down, but it's going to grow at a smaller rate, right? It's not going to be growing as big because all of a sudden you got all this area and you're adding, and that bit you're adding on is getting to be less and less. So the increase in the rate of change of area is probably going to change. It's not going to stay 32. And the same thing with this, okay? So at that instant in time, that's what we get. Now, if we would have done decreasing, what would have changed? Those two there would have been negative, right? Those both would have been negative. So now you'd have had -4 plus -4, so it would have been, the perimeter would have been decreasing at 8 inches per second. Now it makes sense that that number's the same, okay? Well, that both of them are, because both are doing the same. So we're going this way instead of that one, okay? And that would have been -12, -20, that would be -13. Sometimes you get one's negative, one's positive. All right. Let's see what else we have here. Okay, so let's look at this one. So here's how these would normally be working. We won't do all this. A right circular cylinder has a height 10 and radius 8. Dimensions or changes. Usually they don't give that to you right away. Usually it's more like this. Normally they would say a right circular cylinder has a radius that is growing 2 feet per minute and a height that is shrinking 3 feet per minute. How fast is the volume changing when the height is 10 and the radius is 8? So usually they give you these at the end, actually. Okay? So we have a right circular cylinder whose radius is growing 2 feet per minute and its height is shrinking 3 feet per minute. How fast is the volume changing when the height is 10 and the radius is 8? That's how that problem is set. Now, it's really easy to tell these problems from optimization problems, right? Because optimization problems are asking for a max or a min, which is the largest, that kind of thing. These are all about rates, all about rates. This is changing, how fast is this changing? Totally different types of problems. Okay, so what's a cylinder? What's the volume of a cylinder? Volume of a cylinder is pi r squared h, right? That's the volume of a cylinder, okay? So what did they tell me right here? Radius growing at 2. What do I write down? R prime equals 2. As soon as you see a rate, you start writing primes down, right? And the height is shrinking at 3. H prime equals -3. So right away, I write those two things down. Okay? Now, they tell me that they want me to find how fast the volume is changing. They want me to find V prime, and a lot of times I'll write that down and just put question marks because that's what I'm trying to find. They want to know how fast is the volume changing when the height is 10 and the radius is 8. Now the mistake sometimes people make is they want to plug an 8 and a 10 in here right away. Now the problem with plugging an 8 and a 10 here right away is you get V equals 640 pi. And then you try to do V prime. Well, what's the derivative of 640 pi? 0. It always would be. If you plug these numbers into the formula too early, you just get a constant. You get the volume at that point. You can't do the derivative of anything, right? There's nothing to do the derivative of. So we never plug any of these numbers in until after we've done the V prime, the derivative. The only time we would plug something in earlier than that is if it never changes in the problem. If that's a constant the whole time. If that is never changing, if that quantity is never changing, then we could plug it in right away. But in this case, the radius and the height are both changing. So we can't plug those numbers in. They're not constants. Okay? All right, so what would we do? We would do V prime. So let's do it. Now, I would suggest a product rule where I would attach that pi to the r squared. So what's the derivative of pi r squared? 2 pi r prime. Don't forget the r prime, right? This is implicit differentiation. What we have here, to be honest, I probably should write I'm not going to make you write it this way, but I probably should make you write it like this. Because that's what we have. We have an r function and an h function. We have r is changing over time, and h is changing over time. So r and h are like functions. And so that's why when we do the derivative of that, we have to tack on, okay, that r prime. That's really what's going on here, okay? And then, okay, so now that was the derivative of the first. Leave the second alone, the h, plus pi r squared left alone. What's the derivative of h? H prime. There you go. Now I can plug all my stuff in, right? So now I can go, okay, so v prime is 2 times pi. What do I put for r? 8. R prime, 2. H, 10, plus pi, r's an 8, and then h prime, -3. And so I get 80 times 4, what's that, 320 pi. Now we could go to decimals here, it'd be fine. 64 times 3 is what? 192 minus 192 pi. So that would all end up being 128 pi, and this is volume, so what should the units be? Feet cubed per minute. And it's easy to see why, because the 8 was in feet, the 10 was in feet, and the 2 was feet per minute. So feet times feet per minute would be cubic feet per minute. Okay? So the volume is increasing. The volume is increasing at 128 pi. I think I did that right. But you can get to a decimal, but you don't have to. Okay, you get to use your calculator. All right. So if we want to take any notes, let's do. I think I've got a version of this here. I thought I did. Nope. That's not what I want. Okay, let me. I know I've got this here somewhere. Here we go. All right. So if you want to write this down, and again, it's a little bit like a recipe to follow, kind of like we did with optimization. I think it can be helpful. It's up to you. But in these related rate problems, it's typically good to identify the various amounts and rates in the problem. So just like the last problem, we wrote down R prime equaled 2, H prime equaled -3, R equaled 8, H equaled 10. V prime's what we were looking for, right? That kind of stuff. So we write down and we identify those. And oftentimes the next step is to draw and label a diagram. Now sometimes that's your first step. Sometimes you draw a diagram and start labeling it, picking out what to label the things, and then you write down your R primes or X primes or Y primes or whatever. Okay, so sometimes 1 and 2 kind of go together. All right? Then once you see what you have, obviously in that last problem we had volume, we had radius, we had height. Well, what's the obvious equation? The volume of a cylinder. So we wanted volume V equals pi r squared h. We want some equation that relates those variables that I'm given in the problem. Now here's what I was talking about here in the blue. Don't plug in any values that change until step 5. Okay? If you have some value that's going to be constant the whole time, then that's fine. Go ahead and plug it in early. But you can actually wait on it also. Let's say you got a length Z that's never going to change. You leave it as Z in the problem. You do your derivative, you get a Z prime. What's Z prime of a quantity that if Z never changes? it's 0. And so it ends up wiping itself out anyway. So you can kind of do it either way. All right, step 4, differentiate, which means take the derivative of both sides with respect to t. And that's what we've been doing, and that's why we tack on these x primes and r primes and h primes and l primes. And you're going to have those throughout these problems. W primes, you're going to have it all. Okay? And once you've done that, then you just substitute in all the stuff you've been given. And the easiest ones are the ones like we just did, where they give you everything. They give you all these numbers, and you just plug them all in and you solve. And there you go. And then make sure you got the correct sign. Make sure you got, if you're finding a quantity that's decreasing, you better come up with a negative rate. Right? And then also units. Put the right units on. Okay? So, different set of steps than when we were doing optimization, but yet it involves a derivative, right? It involves a derivative, just in a different way. We were using derivative in optimization to find when the slope is 0, to find when the slope was undefined, because that's when max and mins, that's when high and low points occur, and we were interested in high and low points. These problems, we're interested in how fast quantities are changing, but that's also what the derivative does. It tells us how fast a quantity is changing. Okay, so let's do, let's go back to this. Okay, so let's go. Here's what I want to go to. All right, so here's a problem. 6-meter ladders against a wall. If the bottom is pushed or pulled at 1/2 meter per second. Now let's say we're pulling it away from the wall. So it could be pushed or pulled, but it's moving away from the wall at a constant 1/2 meter per second. How fast is the top of the ladder sliding when it's, and let's just pick one of these, they give you 3 different ones. Let's just say when it's 3 meters up the wall. Okay, we're going to ignore those 2. Okay, how fast is the top of the ladder sliding when it's 3 meters up the wall? Now they've drawn a picture, and it's kind of fun because we can kind of see this happen, but how would you be doing it if this was a quiz question? Well, you would draw, so we said draw and label a diagram. That was step 2, actually. Like I told you, 1 and 2 kind of go together. So here's how I would draw this. I would say, okay, I got a ladder. It's sliding. A lot of times I'll put arrows on to indicate the motion of what's happening. Now, do you notice how they labeled this as X and this is Y? Even though it said, how fast is the ladder top sliding when it's 3 meters up the wall? Now, what value is that going to be? But the danger is, for what people want to do sometimes is they want to put a 3 here on their picture. And that's where you get in trouble. Because that's changing. So we don't want to put a 3 there. We want to put a variable there. Because this length is varying. Right? This length is going to vary. So I want to label it with a variable. This length is varying. I want to label it with a variable. What about the ladder? What about the hypotenuse? That is going to be constant. So that's when it's okay to put a 6 there. Okay? Now, we're also going to do some problems where we're going to say one car is driving this direction at 60 miles an hour and one car is driving this way at 80 miles per hour. How fast is this distance between them changing? Well, in that case, you better label this X, Y, and Z, because all 3 of those are changing. As X moves and Y moves, Z is moving too. So in that case, you would need all 3 of those to be labeled as variables. Okay? But not in this case. All right, now step 3 was write an equation. Now, step 1, identify the different things. So, what are we trying to find here? What are we trying to find? We're trying to find how fast is the top of the ladder sliding. In other words, how fast is this distance changing? Y prime is what we're trying to find. What do we know? X prime is 1/2 meters per second, right? We don't have to put the units on, that's fine. What else do we know? Well, the ladder's 6, and we got that in our picture. Y equals 3. See, it's okay to put it up there. I just don't want to put it in my picture because I'm about to go to step 3 now. Step 3 is write an equation that relates those things. Well, what's the obvious equation that relates x and y? X squared plus y squared equals 36, right? X squared plus y squared, that's the obvious equation that relates x and y. Now, we're going to get into some problems that will involve a right triangle. I can think of one I'm going to show you here in a minute that's got a searchlight. And it's got this is rotating. Okay? Right? And so you got something going along here. And so now as this rotates, this length will change. Right? This length may be changing. This theta is changing. So all of a sudden now you want to involve this height and you want to involve theta. Now you might be talking cosine. Might be the equation you want. Because you got to get this and theta involved. Well, that's adjacent over hypotenuse. So you might want to do cosine of theta equals this over this, that kind of thing. So there's always an equation you can put together that relates the quantities in the problem. In this case, it's just x and y, so it's Pythagorean theorem. All right, so now what's next? Step 4 was do the derivative with respect to t. So what's the derivative of x squared? 2x, x prime, plus 2y, y prime, equals 0. Now, let's imagine you would have not put the 6 on there, and you would have called that z squared. Let's imagine you would have done that. Well, right now it would have worked out fine because you'd had 2x x prime plus 2y y prime equals 2z z prime. Okay? But what is z prime? What's the rate this is changing? 0, because it's not changing. So this whole side would have ended up being 0 anyway, right? So even if you'd have done that, you could have ended up okay, all right? Anyway, back to this. Let's start putting stuff in. So what's x? Huh? No? Was x? This was y. Let's just leave that blank for a minute. What's x prime? Now, again, is it negative or positive? We're pulling it away from the wall. So what's x doing? This is the question you always have to ask yourself. It goes back to the chart, doesn't it? X is increasing. So therefore, x prime has to be positive. If we were pushing the ladder towards the wall, x would be decreasing, then x prime would have to be negative. Okay? So x prime is 1/2 plus 2. What did we say y was? 3. What's y prime? Is that what we're trying to find? That's what we're trying to find. So we don't know. So let's just leave it y prime. Okay, so we got a problem. We got an x that we don't know. How can we get that? Yeah. Take this. Put it right there. Sometimes that happens where one of the letters you don't know, but you really do know it, because at the instant, they say at the instant the ladder is 3 meters up the wall, we'll know how far away it is. We'll know what x is, because we'll have that original equation in. So what you do is you just take your 3 and plug it in there. So you get x squared plus 9 equals 36. You get x squared equals 27. So x would be square root of 27. Okay? So now we get our calculators out. Of course, the 2 times 1/2 just cancels, so we got square root of 27. You could just solve it at this point. Plus 6y prime equals 0. 6y prime equals negative square root 27. Y prime equals negative root 27 over 6. Go ahead and divide that out for me and see what we get. And this would be meters per second. What is it? Negative 0.866 meters per second. So it's coming, right? This was 0.5, so it's coming down faster than what it's going at. Okay, so let's let this run. Okay, so if we just let it go down, okay, you see it at the top it's not moving very fast, and as it gets towards the bottom, it's faster and faster and faster. Remember, this is a constant. If you watch this, that's constant, right? That's just moving at a constant 1/2 meters per second. But it's pretty slow here, pretty slow in the beginning. And then, okay, and at y equals 3, boom, right there. Okay, and where's my answer? Why don't I get an answer there, Richard? Negative 0.86. Okay. All right, so that is called related rates. Now we have several different types of problems. Here's a boat. Here is a boat coming in. The rope is being reeled in at a constant 2 feet per second. They put those dots there so you can see that that's coming in at a constant rate. Okay, 2 feet per second is pretty slow, but X is now all of a sudden it's faster, 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 faster. Okay, so how fast is the boat moving? That would be the change in X. How fast the boat is moving, it'd be how fast X is changing. Okay, here's another one. We're going to put water into a cone. Okay, so water's going into a cone at a certain rate, 2 cubic centimeters per minute. So the volume is changing. So we know V prime, but so is R and so is H. Now cone problems are kind of a special scenario. Cone problems are the one time we will usually try to get it in terms of one variable, because it gets a little too complicated if we don't. The derivative just gets a little messy. So what we typically do, it says that this cone is 16 centimeters height and radius 4. Well, if we draw this, so if that is 16 by 4, we use a little bit of geometry here. Remember similar triangles? Here's R and H. R over H is going to equal 4 over 16. Or R is going to be 1/4 H. Right? As that water fills up, 4/16 just 1/4, multiply the H over. So as that water fills up, it's always going to stay in that ratio of the radius being 1/4 of the height. And why that makes that nice is when we do, this is the volume of a cone, by the way, and you'll do a bunch of cone problems, so you'll get used to that. But when you do the derivative here, you would have to do a product rule. And you'd have R primes and H primes. We usually don't have enough information to plug into that, and it gets pretty complicated. So what we do instead is we take this and we substitute it in there. So we get V equals 1/3 pi. We have 1/4 H squared and then H. And so we can simplify that. 1/4 squared would be 1/16 times 1/3, that'd be 1/48 pi. And then we get H squared times H, we get H cubed. And then we can work with that, and that's a lot easier. Okay, so if there's I'm not sure if there's a cone problem on your first set of exercises. I don't think there is. But that's one of the situations where we will do that. Okay, so when they get a little trickier is when you have some extra variables that you don't have enough information to deal with. You can eliminate the variables down a little bit, and that's when we can do that. Okay, here's kind of a fun one. I like to watch this guy walk. Okay, you got a bunch of changing quantities here. You've got the length of his shadow is changing at a certain rate. Him walking at a certain rate would be the green. That'd be the change in the green. The length of his shadow is a rate, and the red dot is a different rate. That's the rate he's walking plus, right? The tip of his shadow is moving at a certain rate. It's how fast he's walking plus how fast his shadow is growing. Okay? So that if you call this S for shadow, this would be S prime, call this X, that'd be X prime, and then the tip of the shadow would be even, that'd be those two added together. That would be how fast that would be. And so anyway, so that's another scenario. So there'll be a bunch of different ones we'll get into. All right, before I give you your homework here, let's pull out the business packet. So we're going to do a few more in the business packet. So you're going to get a mixture today of some max min and then these related rates. Okay. I just want to help you get started. I will post the answers to the business packet, I think. I haven't decided for sure how much help I want to give you here. So where I write today's assignment under today's date, Monday the 15th, if I'm going to post them, they'll be posted there. Okay, let's look at problem 15. So your assignment is basically the business packet, all the rest of the circled problems. So you did 3 and 8 already. And so we're going to do the rest of the circled problems, which takes you over onto the other page, 19 and 20. Okay, so that's most of your work's actually going to be on the max min. So we learned about this new thing, related rate. We gave you a couple to get you started on that, but most of our work's going to be in the max min area. So let's talk about 15 here, just to get you started. It says a commodity has a demand function modeled by little p equals. Remember, little p was what? They called it the demand function, so did I, but I called it something else. Price per unit. Okay, so that's the price per unit. And then a total cost of this. What price yields a maximum profit? Well, remember, profit is what? Now, revenue minus cost. And how did you get revenue? Number of units, X, times your price per unit, and then minus, right? That's your revenue. So your revenue is the number of units times your price per unit, and then minus the cost. Okay? So they gave you the demand function, so that's the little p. So you simply need to set up your profit equation. So they want the max profit. Before you do max profit, you got to have profit equals. So you're going to have big P equals X times that minus that. There's going to be your profit equation. And now you can go about doing the derivatives, setting it 0, right? Finding your max. And then they talked about when the profit is maximized, what's the average cost per unit? Remember, average cost per unit was a total cost, which they gave you, big C, divided by X, right? So total cost divided by X. And so once you find that X, you just plug it into that. Okay, so just to remind you a little bit about that stuff. All right, so we're going to do the circled business packet problems, and then section 4.5 in your book, 4 and 7. Okay, so finish the business packet, the circled ones, and do 4 and 5, or excuse me, 4 and 7 in section 4.5.
Can I get a business packet?
Yeah.
Thank you.